Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It is my sincere pleasure today to welcome back Amy Carlson to MSR. Amy has been an intern with our group twice, and the last time she was an intern fellow. Both times she did fantastic work in the mobile space, first with the Fathom way of visualizing your search results for the local Puget Sound web page, Yellow Pages, and had a paper at Chi from that. And this last time she built a system called Courier with Brian and Greg, and it was a very successful way to take all your information with you on your mobile smartphone. So I'm sure she's going to talk about those, although I'm not sure. But she's probably also going to talk about her dissertation work, which is on one-handed interaction with the mobile phones. So without further ado, I will leave it to Amy to let you know what she's up to.
Thank you, Mary. So good afternoon, everybody. I'm Amy Carlson from the Computer Science Department at the University of Maryland and Human-Computer Interaction Lab. And I've been working for the last few years on developing better understanding and support for one-handed mobile computing. And so I have been working on this for several years, and so I'm going to give an overview of most of my work, but go into detail on just a few select projects, and then can answer questions about the others if there are specific questions. So I'm going to start out just by giving a brief appeal for why we should even care about mobile computing in the field of human-computer interaction. So not only are these devices becoming more capable and powerful computing platforms, but they're being used for an ever-widening variety of tasks and roles that have been traditionally served by other appliances and devices. And they're also beginning to dominate in the arenas of voice, text, and web connectivity. And of course, they're able to do so because there are more hands than both landlines and PCs combined. And then we're also seeing a shift from them being used as simple tools for voice communication to, personal portals onto the information world and sort of full expressions of self. And so, just as we're sort of HCI is maturing into an established research field, we're seeing, we're on the dawn of sort of a new era of personal computing that's going to have a lot of interesting challenges and opportunities in user-centered design. So with that out of the way, speaking of personalization, this is just a small sampling of the huge numbers and varieties and styles of mobile devices out today. And some have keyboards, some don't, some have touchscreens, some have QWERTY keypads. But we can, even though despite these sort of fundamental differences in design, we can draw common design challenges from the fact that most are designed to be small enough to be carried with users throughout their daily activities. And these constraints on size necessarily limits their input and output capabilities, which presents challenges for usability and UI in terms of effective presentation, navigation, and control of information. And then at the same time, mobile scenarios place significant demands on users' mental and physical resources, and users may not even have both hands available. They may be carrying other items or using a hand to navigate their environment. And so it's this particular constraint of only having one hand available sometimes to use a device that's been the focus of my own research. So for the purposes of this talk, I'm going to simplify this vast design space by claiming that most fall into two general categories. Those that take after traditional cell phones typically feature a keypad, and since they don't typically have a touch-sensitive screen, interaction is performed indirectly through keypad-mapped functions. But they also, this limits some of the expressivity of design, but they tend to be small enough to be easily managed with a single hand. Then there are those that take after traditional personal digital assistants, or PDAs, and while they may have a small number of function buttons, the primary input channel is a touch-sensitive display that assumes input directly with a stylus. And so this allows them to be more versatile and expressive interfaces, but since they can be larger than phones and have targets that are either too small or too far to hit with the thumb, you generally need two hands to use them. And so it's this particular class of device that, at least now, requires some of the most attention in supporting one-handed use. And there has been quite a variety of research on one-handed interaction, but the majority have focused either on a particular technology, like using spatial position with using accelerometers as an input parameter, or particular tasks like text entry or music play. And then then other than the BlackBerry shown at the upper right, there have been few that have focused specifically on thumb interaction, and the few that have existed have basically focused on a specific set of tasks and have been quite particular in the terms of the tasks they support. So it's been my guiding question has been whether thumbs can be used more in a more general way. And I'm focusing on thumbs because thumbs are very versatile and they're a very natural way to interact with devices, especially when you're looking at a screen. And so it's this kind of natural interaction that I'm interested in, not, you know, the kinds of props that might be used to take what's effectively a two-handed interface and making it one-handable. So, as I said, sort of my guiding principle has been, can we create designs that are more generally able to make thumbs used as an input across a wide variety of forms and for a wide variety of functions or tasks? And I've approached this from sort of the directions of theory and practice, which I consider my foundations and applications. And in foundations, I've looked at some fundamental human factors involved in supporting or one-handed use or in users' ability to perform tasks with a single hand. So I've looked at how users currently are using devices, how they want to use devices, how they're physically capable of using devices, and then taking lessons learned from these studies, seeing how they apply in practice to real-world applications. So navigating local data sets, searching large unfamiliar data sets, and then finally have looked at broadening the application of these findings to support the full range of tasks users might want to support on their might want to do on their devices, and in particular looking at an interaction technique that would allow users to control rich stylus-oriented touchscreen designs with large thumbs. So this gives the stars give, if you can see, a general idea of where I'm going to be spending my time during the talk, with the more stars indicating more time. So when I started out my work, I looked at sort of the how and why of hand use in mobile device use. So I went down to BWI Airport and I watched users using their phones. And I recorded what kinds of devices they were using, whether they were standing, walking, or sitting, their level of mobility, that is, whether they even had one or two hands available, and how many hands they were using to interact with their device. And what I ended up seeing was mostly phone use, because that was just the population that I was seeing, and that the majority of use, 3/4 of it, was done with one hand. But I also saw a relationship between the level of mobility and the number of hands people were using. So the more mobile a user was, the more likely they were to be using one hand. So walkers used one hand more often than standers more often than sitters. But it was also the case that the more mobile a user was, the more likely they were only to have one hand available. So while this was motivating, it didn't give me any idea about what the directionality of this relationship was. Yes?
Did you also kind of break it down along the lines of the devices that they use? Because some devices have a QWERTY keyboard and others don't, and the ones with the QWERTY keyboard are probably more likely to be used rather than one.
Absolutely. So it turns out that I only classified things in the broad range of sort of phones versus PDAs or BlackBerries. And it turns out that out of 50 observations, only 2 of them were PDAs. And so there was very little, and both of those were being used with, I think they were BlackBerries, and they were being used with, actually one was a BlackBerry being used with 2 hands and one was a PDA. And so the others really tended to be cell phones. And I was recording the interaction of dialing or whatever they might have been doing on, but then they usually were talking. And so my assumption is that they were 12-key keypad devices and not QWERTY keypads. It was, people were doing sort of calling type things. So, however, the next slide might be more interesting to you. So since I didn't have any information about the directionality of those relationships, I then did a web survey to ask users directly about their, for a set of 18 tasks, how many hands they're currently using, how many they want to use, and the motivations for their choices. And this is sort of a very simplified version of my results that shows actually, though, quite nicely some of my major findings, which are at least looking at, so one hand is in green and 2 hands is in blue. And for the majority of tasks that I considered writing tasks, so this might have been text messaging or even entering URLs or things that required writing, people are currently using 2 hands mostly more often than one hand, whereas for reading tasks or browsing tasks, they're more often using one hand. And the data I have actually is broken down by device type, but I'm not showing it in this particular representation. But then when I looked at how users want to use devices, for all of these different tasks, users claimed that they would prefer to use one hand more often than they were currently able to. And so even though you're not seeing the breakdown by device, and I actually have a slide at the very end if you're interested in that, this was even more so the case for touchscreen-based devices. But I did actually classify those that have QWERTY keypads, those that just had touchpad or just full screen touch screens, etc. So, but for almost any device, regardless of whether it had a keypad or a QWERTY keypad, if it had a touch screen, they're more likely to want to use one hand more often than they were able to given the current technology.
In the survey that you put online, did you ask the question only between one-handed and two-handed use, or did you also ask about maybe other input methodologies altogether, like for RPC type functionality and maybe even speech input?
So people suggested, so I didn't actually prompt them for things like speech input. And when I said, so two hands, I guess I assumed when people were using, when the device they were talking about was a pocket PC type device, I assumed that two hands was with the stylus, but I didn't have them specify. I did have them specify what kinds of input channels their device had. So does it have a touch screen, and does it have a QWERTY keypad, and does it have these things? But I didn't say when you're using it with two hands, is that for text entry versus using the stylus? So I don't have that data. Although the second point, your second point was.
You asked potentially about other methodologies like speech recognition or other.
So I didn't ask specifically about speech recognition or other input technologies, but I allowed people to offer ways in which they thought they might. These devices might help them do their job or whatever task, and several people actually mentioned voice recognition or voice input, and so I took that as feedback, but it's not something I prompted them with.
Did they mention it as something they already do use or something they would like to use?
It's something they would like to use.
Okay.
So if we, looking at why it might be the case that touchscreens support one hand so poorly, you see that this old version of PC contacts, and I know that the new version has been adapted, but this is just an example of a kind of application that almost cannot be used with the thumb because the targets are all too small or too far to hit with the thumb, and it gives some idea of what the challenges might be for taking what is essentially a two-handed design and designing it for one-handed use. And then it's fair to ask why we should even care about touchscreens, because they're actually quite a small portion of the population or of the market share today. And when I started my research, I would have claimed, yeah.
So you're claiming 3% of cell phone market, or 3% of what?
I think...
Because that seems way high. Like I was thinking like 0.01% of the cell phones.
I have to go back to my resources. This is something I came up with recently, and it was a respectable resource, but I think it was of all mobile devices. So it wasn't just phones. It was including PDAs and handheld, I guess, pocket PCs and pocket PC phones. So I'd have to get back to you about that. But it was a reputable source that basically said that's the percentage of touchscreens found in the market today. So this could even be worse than this, perhaps. But I would have claimed that, when I started this, even the minority of users deserve some, assistance in better access to their devices and to their information in the way they would prefer. And then I also would have claimed that as these devices get more powerful, people are going to want pixels. And so I didn't think that they were going to go away. Maybe they're not going to dominate, but they're not going to go away. But then, of course, some of the buzz around some of the new touchscreen-only phones coming out do have some experts predicting that this percentage is going to rise dramatically over the next few years. Yes?
I think most touchscreens today demand that the eye look at the screen, which when people are walking, like half your audiences, does not seem like a smart thing to do.
That's true. That's true. I mean, as I mentioned before, as you're mobile, you've got physical attention and visual resources that are being I guess, demanded for. And so yes, I mean, a touchscreen design does not have any haptic feedback, and so it really requires your full visual attention, and so there are reasons why it doesn't support mobility as well as button-based interfaces. That's absolutely true. And there are reasons why people think some of these phones coming out will fail in that arena. So now that I at least had some motivation for why that people already were using devices with one hand, and they wanted to use devices perhaps even more so than they currently were, I wanted to look at what some of the physical characteristics were and physical limitations might be for supporting one-handed use. So there had been studies that had looked at the size that touchscreen targets would need to be in order to hit them reliably with a stylus. So this is a PDA with a stylus. And then there had been studies for index fingers on kiosk-type touchscreens, but no one had ever looked at thumbs on PDAs, which may not be that different than fingers on touchscreens. But it turns out I thought there could be a very real difference, since thumbs are larger than both a stylus and an index finger, but also there's the added complexity of managing the device in the same hand you're interacting with the screen. So I ran a study and had users perform different types of tasks, both single target tasks like hitting a button or a checkbox, and then multiple target tasks analogous to what might be numeric entry or text entry. And this is just a graphic of the results for a 6mm square target, where you see only the hits within the gray square bounds were correct. And so this gives some idea of the fact that this was a difficult task for users, given the resistive touchscreen technology. And then this graph shows that as target size increased, not surprisingly, error went down. And for both speed and preference and error rate, we saw diminishing returns after 9.6mm square. And so our conservative recommendation would be that 1 centimeter square is a reasonable recommendation for thumb targets designed for thumb use. And it turns out there has been an internal Microsoft recommendation for 1 centimeter square targets for quite some time. But from an outsider's perspective, it wasn't clear whether that was based on empirical data or intuition, or whether that was mostly assuming index finger-based input. And so this was just sort of validating that recommendation and giving some empirical evidence for that recommendation. And so this recommendation also isn't just significant for future designs, but also explains why designs like the Pocket PC 2003 Context is so bad at supporting one-handed use, because there's not a single target on the screen that would be considered large enough to be hit reliably with a thumb.
I don't know enough about ergonomics, but is it linear from the sort of distance of rotation of the thumb?
Linear in terms of...
is it constant across the screen?
So in this study...
To where the thumb is based.
Right. So we did look at... I actually have compressed this visual to a square, but there were actually 9 locations in the 240 by 320 pixel aspect ratio of the device, because we thought there might be differences based on location, and statistically there was no difference in the sizes, or we didn't see any difference based on region. So I was surprised by that, but there you have it. So that gave information about how the larger size of thumbs interplays with resistive touchscreen technology. But then I wanted to know in general how motor capabilities, or I guess biomechanical restraints, might affect how well users can interact with targets and do target acquisition tasks based on what the size of the device, perhaps, or the movement direction of the thumb, or the interaction location on the surface of the screen. So I identified 4 different devices found in common use, at least at that time, and this was fairly representative of a range of devices even found today, from small to large in different shapes. And this shows them in hand to give you an idea about their relative sizes to one another. And it turns out that devices like this, with screens and buttons, communicate to users valid input areas. But my goal was to have task performance communicate or suggest where valid input areas on these devices should be. So in order to prevent these kinds of superficial design features from biasing my results, I created blank slate models of these. and affixed my own set of grid of targets to them. Now, right about now, you might be thinking this is looking a little extreme for the kind of questions we are asking, and I assure you that you're probably right. But we were very excited, I was very excited, my advisor was very excited about the kinds of data this would give us. So forward we moved. So we used a 3D spatial tracking system, positioning system, which was able to give the precise spatial locations of light-emitting diodes, which we affixed to the surface of the devices to define a frame of reference, and then to the tip of the user's finger, so that we could track the motion trajectories of the thumbs over the surface of the device. And then we did, I ran a formal study having users do reciprocal tapping tasks across each of the 4 devices. Each task, users were either moving up to down, left to right, or along one diagonal or the other diagonal. And then in all distances, both 1 and 2 taps away across the surface of the device, so 2 targets away rather. And then in addition to this kinds of this motion trajectory data, we asked users to tell us what areas of each device were both hard and easy to interact with. So to derive this average time from this motion trajectory data, I extracted the middle 3 seconds for each trial, 5-second trial, and then used just standard MATLAB functions to identify the minima as taps. And then I did verify it using this same type of visualization to make sure that things weren't missed, any taps weren't missed, and then calculated an average tap speed just from the number of taps that they performed in the time period that I analyzed. And then I revisited my questions, does device size affect performance? And so I analyzed the movement data and the task time data across comparable regions across the 3 largest devices, and in fact found no significant difference in trial times. And so this seems to suggest that that device size doesn't inherently affect performance, but I would be cautious in suggesting that they're equivalent across devices, because larger devices, we observe much more grip readjustment, which has implications for usability, and larger devices also tend to be heavier, so may cause more strain over time. But in terms of raw speed, we saw no difference in time between the 3 devices. In terms of movement direction, for all of the devices, movement in the up-down direction was not significantly different in time to left to right, but that movement along the green diagonal was significantly faster than that along the red diagonal. And so, since all our users were right-handed, this corresponded to a very natural rotation about the base of the thumb versus quite the opposite, which was the hard or slow direction. So then I also looked at whether, does the area of interaction affect performance? And I looked first at subjective preferences, and users suggested where they thought it was easy to interact with, indicated by the darkest regions on the devices. And we see that users were favoring sort of a central region of each device, but that also encompassed a larger percentage of the area than for the smaller devices than the larger devices. And then we took the subjective preference data and segmented the regions of each device by what we thought would be hard, medium, and easy for users to interact based on their feedback, and looked at whether there were significant differences between the task time data in these regions. And we didn't find any for the small device, indicating users were generally comfortable interacting with the full area of the small device, but that as the devices got larger, we did see significant differences between these regions. And this not only meant that areas that were too far to be hit with the thumb were slow and hard to reach, but also those that were too near the base of the thumb. So we can derive some design guidelines from these results. For one, if you're considering movement direction and you want, it's important to recognize that the diagonal that's easy for right-handed users is going to be the worst possible direction for left-handed users. And so in order to support the broadest range of users, it'd be important to avoid diagonals for repetitive tasks like numeric entry or text entry. Yes?
Everything is software. Can't you just adjust the device for right-handed or left-handed people?
Well, so it turns out, in terms of diagonal use, is that what you're saying? So I guess the problem would be, say it's say you came up with a new text entry method that for some reason favored diagonal axes in one direction or another. Then you're probably not going to be able to have to flip it entirely for the other type of user. And so it's those kinds of situations where, I mean, of course we're going to all make diagonal movements. This is not to say avoid diagonal movements in general, but if it's the kind of thing that might build up over time or, you know, might become a significant portion of a user's experience. But certainly, as you'll see, one of my techniques later, in most of these, most of my work, I've looked at right-handed users just to make sure that, you know, I'm not, there aren't artifacts that I'm not taking into account, but I assume that for certain designs it's easy enough just to flip it and it'll be valuable for left-handed users. So I do believe that for certain interfaces that's a fine solution to make it adjustable and simply say I'm a left-handed user. And then I did see that users the area of the device impacted both subjective preference and actual performance. And so small devices were generally easy to interact with, but for larger devices, they favored more compact central regions of the device. And so if by concentrating input targets there, you not only ensure they're all within thumb reach, but also by limiting the total area they occupy, users can maintain a single grip while interacting with them, which may help in terms of mobility. So essentially now I'm moving into the applications area, although which is where I sort of take these findings and see how they apply to real applications. But I will make a reference to a gesture learnability study that I did in parallel with this next set of work. So in my first set of applications that I explore, I was essentially looking at design trade-offs in building interfaces specifically to support thumb use of PDAs. And I took a common domain, which was navigating a set of applications on a device. And in the first design, I figured it was clear that one option was to simply make all targets thumb-sized and within thumb reach. And I'm going to show a brief video, and that was the launch tile design. Oh, but before I do, I'll mention that even though this looks like a very complex or interface, there actually were only 9 real targets that were thumb-sized. So it wasn't that every line of text there was a target. They were actually much larger than that. That was just sort of an abstraction of that data, and you could actually get to the details of that data by zooming into that application. So here we had a landscape of 36 tiles that was zoomable, and you'd zoom into sets of 4 and could pan around by using directional arrows. And then if a user couldn't actually reach the directional arrows for panning, they could use a gesture to sort of physically move the space and pan around. And then they could zoom out again to get an overview of the region or the landscape. And then they could go into applications specifically, and then applications were all assumed to be designed to be completely thumbable. So here. So we'll move forward. So now the second design, we made no specific efforts to put constraints on either the size or location of targets, but instead provided an indirect gesture command language to move an input cursor from one object to another and perform actions on the objects under the cursor. So here we see moving the thumb from left to right, move the cursor from left to right. And so this gesture language, there are 8 gestures, left, up, down, left, right, move the cursor up, down, left, right, and then the diagonals performed sort of abstract open, close commands on the objects. So here we see a video where the cursor actually is starting out in the middle, and so the user sweeps the thumb up and left to move the cursor up and left, and then diagonal to open. And it used a 3-stage fisheye view to show the context of other applications while the details of another. And then, of course, users could tap directly on objects, or if that were the more convenient way of interacting, and if they could reach the object. So now both of these designs come with their set of trade-offs. So for the launch tile design, it would require that all applications actually be redesigned so that targets are thumb-sized and within thumb reach, and can have implications on effective presentation, since it might limit the size and placement of targets. And then with App Lens, since you're moving a cursor around with commands, that could make for slower access, since you might have to move through several objects in order to access the one you're interested in. And then it requires learning this new gesture language. And so we did a qualitative study to have users give their basically their feedback, their subjective feedback about these designs and give comparative preferences. And we found that in general people were very receptive to both of these different designs. One usability issue we noticed was that users were much more likely to tap directly on targets than use either of the gestures that either of the interfaces supported. And so this might suggest that gestures can be used to augment interfaces, but maybe either hard to learn or hard to remember or hard to discover. But these were very informative early studies, and in fact LaunchTile has moved on to become the basis for a startup company, a Microsoft startup company called Zenzui, which provides users a landscape of dynamic web content, a zoomable landscape of web content, very much based on the LaunchTile design. So Applins and LaunchTile looked at the problem of navigating a fairly familiar set of local applications or data items. But as these devices connect to and store much larger varieties and volumes of data, the problem is going to become actually finding data of interest in this large space. And then at the same time, the devices are remaining relatively limited in terms of their input and output capabilities. So as this data space grows, some of the more desktop inspired access models that have been implemented on today's devices become increasingly ineffective. And what I mean by this is for local data, it's usually accessed through either specialized applications like email or folder hierarchies, but as the data set grows and you're looking for an item, it amounts to having to navigate and page through long listings of results. So, and this is because these small screens can only show a limited number of lines per screen. And then there have been solutions for searching for data off the device, but most have been modeled after keyword-based text search. And as we see, you'll see this graph one more time after this, but you'll see that especially for writing type tasks, not only is it just well known that it is tedious to do, but also for both types of device, people are having trouble using it with one hand, which has been the focus of my own research. So it just, mobile devices are not yet very friendly to text entry, and that's still an ongoing area of research. So these approaches, this keyword-based approach also is very flexible and familiar to users, but is primarily focused or quite good for directed search tasks, like I'm looking for Starbucks, and maybe less appropriate for browsing activities that might be particularly suited to mobile scenarios, like I'm looking for an expensive American restaurant near me. And it doesn't they tend to focus on data off the device rather than the large volumes of data that now can be stored on the device, and so doesn't take advantage of some of the processing power that could be better utilized perhaps for providing a better search experience. And so this is work I did here. So my team and I developed Fathom as a single fluid interface that provided dynamic browse and search activities through dynamic data filtering. And by navigating a keypad mapped hierarchy of data attributes, users would navigate a hierarchy of these attributes and would automatically update the results to show those constraints. And then data attributes could also be stored as query search terms to form Boolean queries. And then it also supported dynamic incremental text entry, so that if you started to enter text at this point, the results would update further. And so you might not even have to enter the entire word that might narrow down your search, like STAR for Starbucks. And so the idea was that it de-emphasized text entry in favor of this rapid and dynamic data filtering approach by sort of discriminating characteristics. And we studied this. We wanted to understand what maybe the relative benefits of attribute navigation were versus text entry for both browsing and search tasks. And we found that, indeed, when users knew the exact name of the target they were looking for, like Starbucks, text entry was much faster. But when users just had a set of criteria in mind, like expensive American restaurant, attribute navigation was much faster. And for all subjective preferences, users preferred attribute navigation. And so this was very encouraging that attribute navigation could be a very effective approach for searching these large data sets, especially on devices that were not well suited to text entry. And so this was work that I had done as an intern the summer of 2005 at Microsoft Research, and we did focus on mobile phones because they're in wider use today, and they, arguably have more constraints sometimes than touchscreen-based devices. But it doesn't take much imagination to think how almost the exact same interface could be applied for touchscreens and could support one-handed interaction. And as Mary mentioned, I was also here last summer and did work on an infrastructure that helped worker productivity by automatically syncing documents to phones that then could be shared in meeting type settings. But that was more of a system and was less characteristic of the kinds of interaction work that I've done for my thesis. So I'm not going to go into detail about that here, but would be happy to answer questions about it or talk about it individually with folks. So both of these past two sort of application efforts had focused on specific solutions to data navigation, essentially, but not information navigation in general. And this is the last time you'll see this. Users, claimed in my survey that they wanted to use one hand for the full range of tasks they want to perform on their devices. So the final phase of my thesis work has been looking at how to provide an interaction strategy so that users can control rich stylus-oriented touchscreens with their thumbs. And once again, we're back to this this slide, where I want to emphasize that I'm not just interested in supporting these kinds of legacy applications, but also to allow designers of future applications to be able to focus on the best presentation of information and the best interaction with when two hands are available, while still supporting control with the thumb. So one thing one characteristic I've noticed from interacting with large devices is that with any particular grip, there's just a limited area of the screen space that is within comfortable reach. And in many ways, this isn't a new problem. And it may be kind of unusual to think about it like this, but this is very similar to the problem of interacting with very large displays. And the key similarity is there can simply be objects that are out of reach. Thumb reach for smaller devices, arm's reach for larger devices. But there's been a variety of research, very successful research in the world of large display interaction. And so my approach has been to see how successes from the very large display, the world of the very large display, can be used for effect for the very small display. And so that was sort of the fundamental approach I took. And so, but it's unlikely that these techniques are going to apply directly. And the reason is that that object interaction has been improved for large displays, often by taking advantage of the indirectness of control between the motor input with the mouse and the cursor output on the screen. And by manipulating this ratio between the control and the display, researchers have been able to essentially reduce the distance between objects or increase the size of the object in motor space to make them easier to hit. But the problem, so one example is object pointing. And in object pointing, once a mouse leaves an object, it jumps directly to the next object in the direction of movement, skipping all the white space in between. And so this effectively brings objects closer together. But one problem in mobile with PDA touchscreens is that users are interacting directly on the screen with a stylus or a thumb, and so they don't have this this control display relationship that they can exploit. But certainly the idea of bringing objects closer to the thumb is an attractive one. And then another solution has been in large display research, has been to provide users a miniature representation of the display space that's local and within arm's reach, and they can manipulate the objects in the display as though with the remote objects themselves. And so this brings all objects within reach, but in large displays you typically have enough real estate, or can at least free up some real estate for this representation if it provides a benefit to users. But in the small display, any kind of miniature you're going to show is likely to include real content. And then objects that were already small in the original display become even smaller in this miniature display. So once again, this doesn't seem to be able to apply directly to small screens, but the concept of having all objects within thumb reach is also attractive. So neither of these these solutions seem particularly suited to the small display, but we had an idea for an interaction technique that could be used to basically address some of the problems that they pose for the small screen. So the technique starts out, the foundation of it is to allow users to define an area of the screen that they're comfortable interacting with. And so this starts out, and this accommodates, users' differences in users' hand strength or thumb length or agility. And so they start out by tapping the area of the screen furthest from the thumb, and then dragging the thumb to the corner of the screen closest to the thumb, thereby defining a rectangle that I call the thumb space. And then the thumb space is partitioned into proxies, each one of which is associated with an object in the original display. So looking along the top row of the contact screen and the top row of the thumb space, we see how the proxies are mapped to the display space objects. So this is exactly like the radar view that you saw a couple screens ago, and there's, to jog your memory, but we're not actually going to show this partitioning because that would occlude the information underneath. I'm just going to show a whitewashed region to show where the thumb space exists. But the problem now is that if someone's going to try to use it like a radar view, they're going to have to guess at where the proxy exists for the object they're interested in hitting. So we solve this problem by providing visual feedback during interaction. So now I'll go through an example of interaction. If we assume the user wants to hit the top contact in the list, pointed out by the purple arrow, the user would reason, well, that's about a fifth of the way down from the top of the original display, so I'm going to aim a fifth of the way down from the top of the thumb space. And the object that is associated with the proxy the user actually does hit becomes highlighted in the original display. And at this particular phase of the interaction, the thumb space is acting like an absolute position touchpad. So with perfect knowledge and perfect aim, the user could access every single object in the display just by interacting with the thumb space. But we see the user didn't have perfect knowledge and perfect aim. So in order to correct this, the user can drag her thumb in the direction that they would like the highlight area to move. So in this case, downward. And the highlight then moves downward. And in this mode, the thumb space is acting as a relative position interaction method, so that if moving the thumb in, say, 10 pixels in one direction or another moves the actual input cursor one direction or another. And so this is what allows users to access, say, proxies that become very small when the display is reduced to a miniature, because the interaction is focused on objects and not pixels. And so it's just by crossing this threshold that the input cursor moves to the next object in that direction. Yes?
I don't know the OS well enough, but does it support hover? I mean, I know the device doesn't, so you're sort of faking out hover.
Oh, so the user is touching the screen at this point. It's a physical drag.
But in some sense, you want to give the user an idea of what they're going to do without actually issuing a select in the OS, right? Or in the app.
So most devices are resistive touchscreen technology, and so you actually do have to touch it in order for the device to know anything. It's a very sort of dumb technology in that sense. If it were capacitive, we could potentially make use of hover and things like that. So yes, if it were possible that you could give users a preview of the original, or the object in the original display that they were about to hit, then yes, we would provide that. But for this particular technology, it wouldn't be possible. Yeah.
Do you find some things aren't possible to touch this way? So if you hit in the corner and the thing you want is further to the left, you move 10 pixels to the left, you go out of your thumb space. Is there a...
Right. So it does turn out that this isn't, that once you have an imperfect selection, you can then need to move outside the thumb space. And so that is definitely a scenario you can encounter.
There's no clutching, in other words.
No. Now, in an original, in a previous design, or actually in this particular design, there was a cancel area, so that if I moved my thumb to the cancel area, I could at least say, oops, that was a bad guess. I'm going to start over and pay more attention. And in later designs, a flick could just for example, move the cursor off the screen, and sort of you can cancel by moving the cursor off the screen with a rapid movement. But so no, there's no clutch, and there may be some ideas for cancel, but that's where it stands. Yes?
Some screens have pressure sensitive, so you might exceed a threshold as a mouse click or something like that.
Right. So I think that
You need a binary of some sort to indicate a choice.
so the choice. So yes. So in this particular for this particular technology, lift was the choice. So once you actually fine-tune your selection and you move the target ends up being over the object of interest, lifting your thumb would perform the selection, and in this case, open the contact. But yes, if there were, when or if these touchscreens are able to take more input, like pressure or hover or things like that, then presumably I can do even better than what I can do with just a resistive touchscreen. Okay. So here's a demo. Oh, no, it's not. There we go. Here we go. So the first thing I'm going to do is define my ThumbSpace. And there I was allowed to, if I had wanted to, I could have redefined it by tapping outside, but that was fine. And now I'm just going to tap the farthest 3 corners. So the upper right, the upper left, the lower left. And now I'm just going to randomly go for the 26th, but I'm off, and I roll my thumb and I move to the 26th. So that's the general idea. So the goals with ThumbSpace were to improve selection for targets that were too small to hit with the thumb and too far to hit with the thumb. And the assumption that was by decoupling the input space, which is the thumb space, from the output space, which is the display space, that I'd be able to remove the dependence between speed and accuracy on characteristics of the targets like size and location. So I wanted to study this. I also wanted to look at whether density played a role in how well users were able to use ThumbSpace in terms of target density, and whether users were even interested or even could learn ThumbSpace, and whether they'd be willing to do so in the future if given the choice. So I'm going to go over this study in very high level because it's not the end of the story, but the idea was I compared ThumbSpace to the reasonable alternative, which is directly interacting with the thumb on the screen. And I looked at 2 different target sizes. The large was the sort of magical 1 centimeter squared approximately that should have been easy to hit with the thumb accurately. And then small was a quarter of that size that was still representative of the kinds of widgets you see in, say, Pocket PC today. 2 different densities and distances, which I categorized as near to the base of the thumb or within easy reach, and far, which were the corners, 3 corners. And the results were that direct thumb interaction was faster, kind of a lot faster, 2.5 times faster. So this was the difference between, say, 8 milliseconds on average, 800 milliseconds on average, versus, say, 2100 milliseconds. But maybe this was at the cost of accuracy. And it turns out that indeed ThumbSpace was more accurate along in the farthest corners or in the far regions. And if we look specifically at accuracy and speed just for ThumbSpace, we predicted that the indirectness of interaction, the thumb space, of the input space and the output space, would make speed and performance independent of size and location. So it was true that for time and errors, they were independent of size. So that was good. But we also predicted they'd be independent of location, which they weren't. It was actually worse with targets that were near to the base of the thumb. And this was because, most likely, that those targets interfered, the thumb space that people were defining interfered with those targets. And the performance was also dependent on density. Dense ones were worse, which we assumed. But it was also true that users did see the value of ThumbSpace, and the great majority of users claimed that once they had achieved reasonable practice, they would prefer to use ThumbSpace over direct thumb interaction. So we didn't give up. I figured that with a few strategic design changes, we could actually create ThumbSpace or make ThumbSpace competitive with direct interaction. And so the first observation was that people were worse at hitting close targets, which we want to make hard things easy, but not easy things hard. So the solution was to make ThumbSpace moded. So users could choose to launch ThumbSpace if they needed to or not. And then the second observation was that users were performing quite a bit of dragging during the adjustment phase of selection, meaning they weren't making very good guesses about where the proxies were for the objects they were interested in hitting, which isn't that surprising because we're not giving them any visual indication as to where they are. They just had to sort of do a mental mapping. So as you see here, the second solution was to provide a faithful miniature representation of the display space. And since users are only launching ThumbSpace when they need to, which is usually for targets outside of their reach, this faithful representation isn't likely to interfere with their interaction. But to help further, we remove the ThumbSpace when during the adjustment phase, when users should be targeting specifically on the input cursor. And then one last tweak was just to enforce that the aspect ratio of the ThumbSpace corresponded to the aspect ratio of the display itself. And this allows the representation to not be distorted and maintains the relative spatial positions between the proxies in the ThumbSpace to as the objects in the original display. So a short video of this redesign. I'm going to try and hit the same 3 targets. So I launch ThumbSpace and I hit the upper left. This is harder to see because it's just the outline. So I'm hitting the calendar and I'm successful. I'm going to go for actually the 26th again, and I have the same problem. I have to move over to move my thumb to the left to hit it. I hit the 24th successfully, and now I'm going to go for the lower left, but I'm actually off again, and I hit Tools, but I move left to move to New. So I, of course, wanted to understand whether this redesign was going to help with accuracy over direct thumb interaction. But it also seemed like a reasonable time to step back and ask, is this even the most appropriate way of interacting with targets on touchscreens in general? So what are the alternatives? Well, 15 years ago, Sears and Schneiderman developed a high-precision technique for accessing targets on kiosk-type displays called the offset cursor. And that presents users a cursor above the finger that they can sort of visually verify that the target of interest is selected before lifting for selection. And then more recently, just at CHI a few weeks ago, Dan Vogel and Patrick Bowdish got a Best Paper Award for what's essentially a modernization of the offset cursor. It's also an offset approach, but one of the drawbacks of the offset cursor was that users had to know they were in that mode and so then aim below the target they were interested in, whereas Shift allows users to aim directly at the target they're interested in, and what ends up being in the call-out is the area under the user's finger with a crosshair target that they can fine-tune precisely before lifting to select. And so both of these actually had a lot more algorithmic details than what I'm suggesting, but those were the basic differences between them. And then there's, of course, peripheral hardware. Almost every device comes with a directional pad, and there are reasons to think indirect interaction might be a good thing. One thing is that it gets the fingers away from the screen so there aren't any occlusion problems. And it also is performed in a fairly compact region, so might be pretty reasonable for mobility and allow you to maintain control over the device during a mobile scenario. And then, of course, the hallmark of the BlackBerry, the thumb wheel, has been very successful, and so that's another potential peripheral hardware solution. So I ran a study to look at these various issues where I chose just the one target size, which was the small size from the previous study, and looked at 48 different locations around the screen, and then looked at 5 different input methods. Direct thumb, where they were just from the previous study trying to hit targets directly. ThumbSpace, where I didn't give them any choice. So I had them interact with all of the 48 targets, but they had to launch ThumbSpace for every one of them, even though I know in general I wouldn't expect users to for a subset of those. And then my own implementation of Shift, and those were the touchscreen techniques, and then the peripheral hardware techniques of directional pad and scroll wheel. And I did look at users performing these tasks while both mobile and standing. So as far as the results are concerned, in terms of speed, once again, direct touch was significantly faster than the other 4 interaction techniques. And the scroll wheel was the slowest, significantly slower than the other 4. But once again, looking at accuracy, direct touch, gained the speed at the cost of being the most inaccurate interaction method. So it had the highest error rate of all the other four, and in this case, it was actually the directional pad that had the lowest error rate. So looking at just speed and accuracy, it looks like shift and thumb space are comparable to one another, and it does. There does seem to be a trend towards shift being faster, although statistically that didn't bear out. So there was also an interaction between input method and the region of the device, and so I wanted to look at this further for thumb space and shift. So looking at speed by region, we see that actually green is thumb space, and you see it up there, was actually slower for all of the regions, slower than shift, but it turns out it was only significant for a subset of those regions. And it turns out, interestingly, that these almost exactly corresponded to those that users said were easy to interact with. So those are likely to be the regions that users actually, over which they define their thumb spaces, and we were enforcing users use their thumb space. So these are just the regions that we wouldn't have even expected users to want to use thumb space. And then looking at the percent correct, one thing I noticed, or I was somewhat happy about, is that over on the left we see thumb space seems to be more accurate than shift sometimes. But it was only significant for the upper left-hand corner region. And then over towards the right of the screen, there are some for which shift outperforms thumb space again. And it turns out those correspond to the lower right-hand corner, which are also those regions that users would have said were easy to interact with. So if we consider these together, these results, it seems clear that shift is outperforming thumb space in the regions that are easy for them to reach and interact with, which are those for which we wouldn't have expected people to want to use thumb space, but that there's a trend towards thumb space being having some advantage over shift in hard-to-reach regions. Now, it turns out that the device I used only had a 2.5-inch diagonal, which is actually smaller than even many of the iPads on the market today and some of the much anticipated touchscreen phones coming out. And so we may see that we may see that actually thumb space has even more advantages once we get to larger devices, and there are some areas that are actually truly out of thumb reach. That's an open question. But actually, this idea of using thumb space and shift in concert was also shared by our users, and we had them rank each of the input methods in terms of preference, and a shift plus thumb space combination was ranked highest. But by how much? Well, I also wanted to understand how many people actually ranked each interface within the top two. And over 75%, or rather 75% of the users ranked thumb space plus shift in combination as their preferred interaction method over either of them individually. And so based on this data, the directional pad was actually quite strong in terms of really error rate, speed, and preference. But given including preference, it seems that users, hardware may be effective, but touchscreens are preferred, or directly interacting with the touchscreen with a thumb. And this was something that I thought might be the case. When interacting with touchscreen designs that are designed for direct stylus interaction, it seemed natural that interacting with the thumb would be appropriate. But it's also true, and the BlackBerry is a good example of the fact that the right hardware plus software solution can also be very effective. And the directional pad in our data was quite effective as well. So it's not a black and white solution that interacting with the screens directly is preferred or should be revered more than peripheral hardware, but there are times where each can have benefits. So to continue this line of research, I would need to actually develop a formal algorithm for partitioning the thumb space into the proxies given any arbitrary interface design. And there are a couple properties that I would expect to want to preserve. I'd want it to be space filling, and that every pixel of the thumb space maps to at least some object in the original display. I'd want to preserve, there are some space filling algorithms do make some odd shapes, but I'd want to preserve the spatial positions of these proxies as the same as those for the objects in the original display. And it may be useful to exaggerate some of the landmarks. So maybe I should make the corners bigger, so that if users were aiming towards the corner, they'd be more likely to hit it on the first try, or the center, or use likelihood, or those areas that are more likely to be hit to make larger. ThumbSpace only looked at the particular interaction of tapping on a screen with a stylus, say, but there are lots of other ways users interact with touchscreens, like dragging or tap and hold for context-sensitive menus. And I have my own ideas how ThumbSpace would be used for these types of interactions, but I would have to implement them and test them to see if they were effective. I would like to see whether we see a greater divide between the advantages for ThumbSpace when the devices get larger, because right now it seems like Shift is doing pretty well. I'd like to explore it for real-world tasks. So great, I can hit a target, but can I enter a full appointment and contacts using ThumbSpace? So it would be important to see that real tasks would be supported. And as one of the audience members pointed out, any interaction with a touchscreen is very visually intensive, and visual resources are something that are certainly at a premium in mobile environments, and there's a lot of demand. And so any technique that is striving for helping mobility, one should try and maybe couple them with things like vibrotactile feedback to help interaction, or audio feedback, or it's possible to incorporate some other input channels to help with the mobility aspect. So overall, with these foundational studies, I've been able to provide some guidelines for developing thumb-oriented interfaces, one-handed interfaces for both phone designs and touchscreen designs. And then in terms of applications, have offered some solutions for both navigation, search, and browsing of real data sets, and then also a generalized technique for using what I consider, rich stylus-oriented touchscreen interfaces with a thumb. So I certainly thank my advisor, Ben Peterson, the members of my teams from the last 2 summers at MSR. The first part of my research was funded actually through Microsoft Research through a grant my advisor had, and then this last phase has been funded through a Live Labs fellowship I have. So thank you very much to Microsoft. They funded me whether they knew it or not. So I thank you for your time and attention, and can take any questions. Oh, yes?
You seem to have ignored the issue of texter thumb, which seems to be heritage of the new hacker's hand. Japanese kids do texting and their thumb goes,
Like the BlackBerry thumb, are you saying? Oh, well, so can I ask you whether you're asking have I ignored text entry, or have I ignored the ergonomics issues?
Ergonomics issue.
Okay, so I haven't ignored them in my head, but I have ignored them in my research because I'm not an ergonomicist. And so the closest I got actually was that study where I had the 3D motion tracking cameras and things like that, where I was actually trying to, in my own mind, trying to come up with some idea for, is there a relationship between how fast a user can perform a task and the biomechanical constraints of the hand, which sort of smacks of ergonomic issues, but I'm not from that domain, so I didn't want to claim any of those issues. But I absolutely agree that that it's certainly very important to be aware of, and if I could, team with people that were really ergonomics experts, I would be happy to. But in my own background, I didn't want to make any claims about ergonomics in my work. Dan. And Mary, you're just too slow. No.
So after the first press in ThumbSpace,
yes,
you then scale the interaction so that when you move I just want to make sure I understand.
Right.
When you move your thumb, you're moving only over a small portion of the larger screen at that point, over the data set, right?
Well, should I be repeating questions? Can the audience hear? I'm just going to repeat that the question is whether when I do my interaction with ThumbSpace, I move from once I move to the part where it's the adjustment phase, I'm scaling the interaction so that the interaction is only happening over a subset of the interaction space. Right. And I would claim, no, that's not what I'm trying to do. It moves from, or the way I would characterize it is that it moves from being an absolute position interaction method to a relative position interaction method. So it's true that, so if I move my thumb in 10 pixels to the left, it's going to move, once I reach that threshold, it's going to move to the next target to the left. Now, it could be that that target is clear across the screen or right next to it or something. So it becomes an object-based input solution that is the threshold is just sort of an arbitrary number.
You're not moving a cursor, you're actually stepping into the object model of the app and moving.
Yes, yes. I mean, the cursor is the thing that highlights or identifies the object I'm interacting with.
This didn't have targets, but it was like a map, and you were trying to pick an arbitrary point on the map.
Right.
Then what would you do?
I would probably not use this technique. Now, so I would use shift. No, well, shift is even, well, so that's an interesting question because I don't actually know exactly what I would do. I think that in some maps, I'm not sure exactly what you're selecting. So if I'm looking at, say, live.com.
Something without any semantics. You can't cheat. I'm saying there's no semantics so that you have to specify an arbitrary point.
But in most map interactions, I've either been panning or zooming. I mean, I'm not sure even with, say I'm looking at, so I'm not sure that this would be the right technique, and I might develop a technique specifically, a different technique for the thumb, since thumbs are huge and you're basically asking for a pixel. But if I think about the interactions with maps on a web browser, even though I'm pointing on a pixel, the interaction is sort of a global zoom or a pan or something. I mean, it's not usually that pixel that I'm interested in. So I can think about ways in which I would, I could drag my thumb to define a marquee of an area like zoomed to perform zoom, say, or pan the space by physically moving it or something. So I'd want to know a little bit more about the task and whether it really is that you care about that pixel. And if you really cared about that pixel, ThumbSpace has not been designed. ThumbSpace has been designed mostly for things that have semantics and some structure. Mary.
Two things. So I think it's ironic that you were inspired by large displays, and you've already given us an empirical inkling that you succeeded in designing something that's better for larger displays. You would beat out every other technique if the display was so large you physically couldn't reach it. Your technique would win. The others couldn't.
Right. So primarily, and this is something where I think that there is a I think shift is very effective for anything within reach, but shift was never designed for reach issues, whereas really my whole claim is that I focused on reach as the problem and taking, and using techniques that have helped with reach issues in large displays and dealing with reach on the small display. And so that's really where I would imagine we'd start to see benefits. And some of the devices, there is this very strong pressure for mobile devices to be smaller. So a lot of devices we see today really don't have that many objects that are out of thumb reach, but say ultra-mobile computers. Now, no one's going to use an ultra-mobile computer because they tend to be, maybe this size, really with one hand. But, there's something in between, like, this Prada phone or the iPod phone or things coming out where I think we are beginning to play with that edge where to control the device with one hand and maintain some stability, you're going to have limited thumb movement, and that's where you might see areas that really are out of thumb reach.
I guess I'm looking at it the opposite way. I think you have a great interaction technique for taking or for a touchscreen large display.
Yes, it's possible you could scale up. I mean, you wouldn't necessarily have to, but in that case, so I guess I would have to ask you, so radar views, I mean, this is very similar to a radar view, where if you have this within reach miniaturization, then you could use a pen or stylus or pointer or something locally. And so it's almost the same technique, but I've added some tweaks exactly to make it, use a very large input pointer, which is the thumb, and things like that. And so it's possible that at that point it simply becomes a radar view, which, I mean, radar views have not been used like extensively and all over, but when they've been studied, they've been shown to be effective.
About some of the individual differences.
it was, so the question is whether I gave up, some of the individualization because I said that the ThumbSpace in the second iteration conformed to the same aspect ratio as the display itself. Now, it turns out that I still let users, it was sort of this little bit weird, confined way of defining the ThumbSpace, in that users were still defining the ThumbSpace, but they would find that it wasn't actually getting bigger in one direction. They were trying to make it bigger, or it was getting smaller. And they were able to actually confirm, once they created it, even with these kinds of constraints, they were able to confirm that that was still representative of a region that they felt comfortable interacting with. Otherwise, they could redefine it. And so it was still customized, but with constraints. Yes?
Sounds like you've got some pretty heavy baggage that are tied to existing hardware. If you had your druthers, how would you change? Do you see the demise of the standard cell phone keypad, which takes up valuable real estate? What about the real estate on the back of most devices that are totally unused? Mm-hmm. What about anything else that maybe goes beyond what you can buy?
Right.
Presently.
So I think that, when you saw all those wires and things, maybe, I'm not sure if you came in after that, but I had a brief foray into hardware and sort of thought, I'm not a hardware person. I'm going to stick with hardware and look at, what are the problems with today's platforms and sort of maybe the next few generations of platforms. But I do think it's a good point that this does not mean that the quest is over, and that certain there has been research in back-of-device interaction, and it has not been shown to be promising in a direction that I would look further, perhaps. People have looked at doing text entry with the finger on the back and various things, or even people have looked at interacting on the underside of tabletop displays, which I would maybe draw a parallel between the two. But things like having, keys are very important. They're important for both eyes-free interaction, and text entry is still, communicating with these devices is a huge, is one of their major uses, and so keyboards and things are very important for these devices. Now there has been, I believe that somewhere there are devices that have some sort of touchpad capabilities integrated with the keypad, so you can use it as a keypad as well as essentially a Synaptics touchpad or some kind of touchpad. And I do believe that once Dan Robbins' zone zoom, where you use the keypad to basically segment the display space into 9 zones and incrementally zoom in, that if you had a keypad and could just use a mouse pointer as though we're on the desktop, might be preferable and might be a very attractive solution, but that just having a touchpad with no other functionality, it does seem like quite a use of real estate that it would need to be overloaded, perhaps, to justify the use in real estate. So overloaded with a keypad. So it's a keypad and it's a touchpad. But I do believe that a touchpad would be very attractive in getting the fingers away from the screen entirely and limiting the total area that you need to move the thumb. And so the question was, what would my preference be? I would, I think there is this tension between screen space and keys. And I'm not sure I have a personal preference for that, although if sort of standard devices were to come out that overlaid a keypad with this sort of continuous touchpad experience, I would revisit some of these issues, because I think there are very real things that can be gained from getting the fingers away from the screen entirely.
What about just suspending the whole screen, say on an iPhone or similar, not having any buttons, suspending them on hysteretic domes, a little click, tactile click? Would that not solve a lot of the problems? You would have the equivalent of hover. You'd be able to have tactile feedback that you actually made a choice. Mm-hmm. You could do skating. You could do acceleration like they do in mice. You could get.
Can I stop you just for a second? I'm not sure I understand. Something domes?
You pushed. Well, sorry.
Yeah. So is this like a vibrotactile feedback based on capacitive?
That's whenever you push a key on a typical mobile device, it gives you a click.
Yes, absolutely.
That's what I was talking about.
Fair enough.
So if you suspended the four corners on such a device that gave you the tactile feedback to know you had pushed through.
I see. So you
Other
basically
than that,
have a
if-
flexible screen so that it...
That's not flexible.
Okay.
You just
Yes.
push the screen and you felt a click if you push it.
Yes, fine,
Okay.
fine.
Sorry.
So actually, so that's fair enough. I'm getting, my brain is jumping to, there's something called vibe tones or something, which actually is trying to give at least vibrotactile feedback to give the sense of these domes for pushing on a touch screen without actually, you're not physically pushing the touch screen, but you're getting the sensation of pushing something. And I think that that has real merit for eyes-free interaction, although you would still need, I mean, the problem isn't just pushing, it's also as you move your finger over the display, and maybe that's what you mean as well, you can actually feel the texture of the display. And so you not only know that you've pushed something.
That's not what I'm getting at. If you had a target that you wanted to hit,
Yes.
you would just instantly create your own small little touchpad in a part of the screen that was not part of that target. And you would skate like you would a touchpad on a laptop. So that would get around a lot of the problems that the offset does, that the one-to-one correspondence in touching does. It looks like it would get around just about all those problems. And you would do scaling and acceleration, much like mice. People like mice to do when they're doing intricate pixel-by-pixel drawing. Everything. So if you have that binary that I mentioned before, that
Right,
one binary,
right.
let's say with one finger that said, where I am is the selection I want to make, whether it be on a pixel-by-pixel basis or an object-by-object basis, you still could make that selection in an area that doesn't necessarily violate the display space you're wanting to look at.
Well, I mean, I think that's a great idea. You're much more ambitious in terms of hardware than I must be jaded. But yeah, no, I mean, some creative ways of using hardware could certainly solve a lot of the problems that I'm seeing using this very basic quote unquote dumb technology to interact with thumbs. Certainly. Yes.
I think you're right that full text entry on the thumb is a royal pain.
Yes.
But for searching, how far can you go with just using the numeric pad and letting the computer figure out the ambiguity? Like Starbucks, instead of SBUX, I type 7289 and figured it out.
Right. I think that actually can be quite. I'm not sure what you mean by how far you can go, but certainly I think that would be a better solution than we actually use multi-tap in our particular scenario. And if we had the capability or the algorithm or the time perhaps to do ambiguity, who cares if Starbucks comes up with Bank of America, if that happened to be also in that text string, because you keep typing until you disambiguate enough that you see the one you want. And so, I would have to do studies, or we'd have to study to see whether that indeed minimizes the total number of keys pressed or whatever entered. But I don't see that there is a great advantage over totally disambiguous text. I think doing the least number of key presses possible to get the desired result to the top is a great solution and would be just fine.
Any more questions? Okay, well, let's thank Amy.